Hello and welcome to part 2 of lecture 23. We're going to continue to talk about some theories of introducing quantum physics. All right. So before in part 1 we talked about black body radiation and the photoelectric effect. So now let's introduce X-rays. All right, something that we all know in everyday life, but when were they discovered? All right. So X-rays were discovered in 1895 by Wilhelm Röntgen. And later they were identified as an electromagnetic wave. So they didn't know what they were. Maybe they thought they were a particle, but it turns out they were a form of light. So X-rays have a higher frequency than ultraviolet radiation and can easily penetrate most materials. So typical X-rays have a wavelength of about 0.1 nanometers. So you can think about how they're almost 1,000 times shorter than the wavelength of visible light. All right, and this is on the order of atomic spacing. Okay, so these things are the size of the distance between atoms. All right, as a result, they can be diffracted by the regular atomic spacing in a crystalline lattice of a solid. All right, so that means that crystals can actually act as a diffraction grating for X-rays. So let's take a look at a diffraction pattern. All right, so we see kind of a picture of one, but let's take a look at the process. Okay, so X-rays are produced when high-speed electrons are suddenly slowed down. For example, when a metal target is struck by an electron by electrons that have been accelerated through a large potential difference, right? So thousands of volts. This very high-speed electron will be suddenly decelerated. Okay, so the figure on the left shows a schematic of the diagram of an X-ray tube. Right, so this is the production of X-rays. A current in the filament causes electrons to be emitted. Okay, so this is just a filament that is being heated up. Electrons are sort of boiling off the surface. Okay, because they're getting so energetic that some of them are able to free. It's really like evaporation in the same way that some H2O molecules, particularly energetic ones, would move away from a body of water. Likewise here, in a metal with all those that essentially sea of free electrons, when you start heating it up, some electrons are so energetic they're able to escape. Okay? All right, and so these freed electrons are then, maybe normally they just sink back down in the metal after they're freed, or they just kind of bounce around randomly and probably end up hitting the metal in many cases. But in this case, they're not, because there's a electric field, because we have essentially, there's an ambient electric field that causes them to be accelerated. Okay? And they're accelerated towards a dense piece of metal, such as tungsten. All right, so this is our tungsten target here. Okay, so we have the electrons boiling off the surface of a filament, being accelerated by an electric field, and crashing into a piece of metal. Okay, and so the tungsten is held at a higher potential than the filament. Okay, so it's going to be the destination of the electrons. They're going to fall towards that higher potential. Okay, because remember, the electrons they essentially fall up in the electric field because they're attracted to the positive charge. So they're going to head towards the higher potential. Okay, so let's take a look at the effect. So the plot of the X-ray intensity versus wavelength of the spectrum of the radiation emitted by an X-ray tube, like the tube we saw on the previous slide. Note that the spectrum has two distinct components. One component is a continuous broad spectrum, like black body radiation, but then there's two big peaks. Okay? So those peaks, what do they represent? So the sharp lines represent radiation emitted by the target atoms as the electrons undergo rearrangement. To see these lines, the accelerating voltage must be greater than a certain value, called the threshold voltage. The continuous radiation is sometimes called the Bernstrahlung, a German word meaning breaking radiation, because electrons emit radiation when they undergo an acceleration inside the target. Okay? So the figure here illustrates how X-rays are produced when an electron passes near a charged target nucleus. So how do we get these well-defined peaks? How do we get the production of X-rays? As the electron passes close to a positive charged nucleus in the target material, such as that solid piece of tungsten, it is deflected from its path because of the electrical attraction to the nucleus, which means it undergoes an acceleration. Okay? If we think in terms of classical physics, any charged particle will emit electromagnetic radiation when it's accelerated. And here, just the act of turning would be a form of acceleration, right? Essentially, this is a little slice of maybe some centripetal motion, thus an acceleration, thus creation of light. All right? However, according to quantum theory, this radiation must appear in the form of photons. Because the radiated photon carries energy, the electron must lose kinetic energy because of its encounter with the target nucleus. All right? So this is interesting because this is telling us that it's not just like the electron is, turning without losing kinetic energy, because we know that's the case. We could throw an electron into a magnetic field and have it turn and accelerate, but it wouldn't lose any kinetic energy, right? But here's the thing. We know that it must lose kinetic energy because it's emitting a photon, and that photon has its own kinetic energy. Okay? So an extreme example consists of the electron losing all of its energy in a single collision. All right? In this case, the initial energy of the electron after it has been accelerated through a potential difference of delta V is transformed completely into the energy of the photon. That would look like this. So this is the energy that the electron picked up by being accelerated through some voltage gap, and that energy of the electron here is going to completely become the energy of the photon, which we could rewrite instead of HF, we could rewrite as hc over lambda, and that's just because, of course, c equals lambda f for photons. Okay. And this equation can be solved to show that the shortest wavelength radiation that can be produced. Okay? And that's this one here, which I accidentally wrote over, so let's get rid of that writing. Sorry about that. So here we see that this shortest possible wavelength light that is produced is going to be hc divided by the energy of the electron. Not all the radiation produced has this particular wavelength because many of the electrons aren't stopped in a single collision. The result is that the production of the continuous spectrum of wavelengths, like we saw in the last graph. All right, so X-rays have lots of applications. They can be used to study art, the deeper layers of art in certain pigments that are based on heavy elements. All right, and we can then also look at the properties of a crystalline solid based on the diffraction pattern. All right, so recall that we can use diffraction gratings to measure the wavelength of light. So in principle, the wavelength of any electromagnetic wave can be measured if a grating having a suitable line spacing can be found. So the spacing between lines must be approximately equal to the wavelength of the radiation to be measured, and X-rays have a wavelength of, as we said before, about 0.1 nanometers. So it'd be impossible to construct a grating with such small spacing because that's an atomic spaced grating. But it turns out that spacing already exists in solids, right? So you can actually observe the structure of solids by basically blasting them with X-rays or with X-rays. Okay, so you're going to produce X-rays, and then you're going to shine those X-rays through your crystal. Okay, so that's what's going on here. We have an X-ray source. Perhaps these are X-rays that are being produced by a tube like we saw before. So we have, so first of all, we create electrons, we accelerate those electrons, we crash them in the metal, that creates X-rays, then we direct those X-rays through some aperture, a collimator, just to make a narrow beam, and then we shine that beam onto a crystal that we want to investigate, and then the photographic film here shows a particular pattern that tells us the structure of the crystal that we otherwise never would have been able to see. We can't look under a microscope and see, right? So this is actually a form of an electron microscope. We're using in this case X-rays, but X-rays produced by electrons to observe something on a very small scale. It's not exactly like an electron microscope where the electrons themselves are being used directly. We'll speak about that in just a moment, but it's obviously a kind of a stepping stone. Historically, it did come first, right? So this would allow for us to understand crystalline structures like this, okay? And how do we quantify the diffraction? Okay, well, we can use essentially a diffraction grading formula. So we'll have some examples of this, some actual numerical quantitative examples that you will solve using the formula below. Okay, and so essentially what this is saying, so suppose a X-ray beam is incident at grazing angles of theta, okay, with a plane as shown in the figure. The beam can be reflected from both the upper and lower plane of atoms. Okay, so those planes of atoms are causing reflection of the light, which we know is actually collision and conservation of momentum of the photons. The geometric construction shows that the beam reflected from the lower surface travels further than the beam reflected from the upper surface by a distance of 2d sine theta. The two photons, right, that's just the path length difference, right? See? The two photons of the reflected beam will combine to produce a constructive interference when this path length difference equals some integer multiple of the wavelength. Okay, so this would be the condition for constructive interference. So what we see here is it's a type, we call it a like kind of X-ray diffraction pattern. This type of light interference is most similar to thin film interference, right? Because we deal with these two waves that are superimposing. These are the reflected beams that are superimposing on each other, and they either interfere constructively, destructively, or somewhere in between. All right, so the technique of X-ray diffraction has been used to determine the atomic arrangement of complex organic molecules, not just inorganic crystals. Okay, so that's all about kind of the discovery of X-rays and their early applications and continuing applications. So let's get into another part of kind of scattering light. Okay, because we just discussed X-rays scattering off of solids, right? Basically scattering off of the nuclei of a solid. But what other type of collisions can photons occur or incur? Well, one of those is something called the Compton Effect. So in 1923, Arthur H. Compton directed an X-ray beam of wavelength lambda naught towards a block of graphite. He observed that the scattered X-rays had a slightly longer wavelength than the incident X-rays, and so the energies of the scattered rays were lower. He found that the amount of energy reduction depended on the scattering angle. Imagine setting up an experiment so precise, right? The change in wavelength between a scattered X-ray and an incident X-ray is called the Compton shift. To explain this effect, Compton assumed that if a photon behaves like a particle, see now we're really starting to kind of take that idea of light as a particle and really help us understand the universe by using that concept. So Compton assumed that if a photon behaves like a particle, its collision with other particles is similar to a collision between two billiard balls. Wow. That means that the X-ray photon carries both measurable energy and momentum. And these two quantities must be conserved in a collision. Oh yeah, indeed. Right? An elastic collision, because that's what we're essentially assuming the photon colliding with some particle like an electron undergoes an elastic collision, and that means energy and momentum is conserved. Okay, so if the incident photon collides with an electron initially at rest, then the photon transfers some of its energy and momentum to the electron. So the energy and frequency of the scattered photon are lower, and its wavelength increases, because that's the only way that photons can manifest a change in energy is to have a change in wavelength. Applying relativistic energy and momentum conservation to the collision, the shift in wavelength of the scattered photon is given by the equation. All right? And so this shows us a relationship between the kind of the angle that the scattered photon is traveling at relative to its original path theta, and then we relate that to the change in wavelength of the photon. Okay, so ME is the mass of the electron. Theta is the angle between, as I was saying, the angle between the direction of the scattered and incident photons. And the quantity H over m naught c is called the Compton wavelength, because this right here has units of meters, lambda. Okay? The Compton wavelength is very small relative to the wavelength of visible light, so the shift in the wavelength would be difficult to detect if visible light were used. Notice that the Compton shift depends on the scattering angle theta and not on the wavelength. Experimental results for X-rays scattered from various targets obey this equation and so support the photon concept, right? So this is really, just like the photoelectric effect was experimental confirmation of the quantization of light into packets called photons, likewise, the Compton effect was further validation of that theory, okay? And again, this shift, we can see, is very small, right? It is a fraction, it's 1,000th of a nanometer. So we're talking 5 orders of magnitude less than the wavelength of visible light. And that's why it only really is perceptible with high energy X-rays. And even then, it's going to be a small percentage change, okay? And that's because the electron, right? That potential energy that the electron picks up and thus the energy that it removes from the photon is always going to be quite a bit smaller than the energy of the light, okay? So when a photon scatters off an electron, the photon loses energy. Is that true or false? Okay, we're just talking about it. Make sure you understand what we're talking about. The answer is true. Yes, it does, okay? An X-ray photon is scattered by an electron. The frequency of the scattered photon relative to that of the incident photon would be less. It decreases, okay? So the photon loses energy after being scattered. Sometimes that energy loss is minuscule, but it's always there. The photon energy E naught, a photon of energy E naught, strikes a free electron, with the scattered photon of energy E moving in the direction opposite that of the incident photon. In this Compton effect interaction, the resulting kinetic energy of the electron would be what? All right. So think about the equation. All right. So the kinetic energy of the electron would have to just to be the difference between the incident energy and the reflected energy, and that's because in this case the photon is going exactly backwards. It was recoiled exactly backwards. So the angle would have been, using the formula, that'd be a cosine of 180. And if I take a cosine of 180 degrees, then that's giving me -1, right? So 1 minus -1 is 2, and that's how I'm getting my change in wavelength. And so my answer then is it's just E naught minus E. Okay, but we'll get some more practice with that with our computational problems in the next lecture. All right, so now let's get on to our second to last topic in this chapter, and that is the idea of the de Broglie wavelength, or the dual nature of light and matter. Okay, so phenomena such as the photoelectric effect and the Compton effect offered evidence in the early 20th century that electromagnetic radiation and matter interact, that when they interact, the light behaves as if it was composed of particles having energy HF, right? So those are photons of energy HF. And momentum H over lambda. In other contexts, light acts like a wave, exhibiting interference and diffraction effects. So we definitely have this duality then of light. Light can be a wave sometimes, it can be a particle other times. In general, light behaves like a wave when it's in a vacuum, so a diffraction pattern. It's not interacting with the solid, it's only interacting with itself, and it's displaying its wave-like properties. When light interacts with particles and solids, it behaves itself like a particle. Okay? So the apparent duality of light can be partially explained by considering the energies of photons in different contexts. For example, photons with frequencies in the radio wavelength carry very little energy and it may take 10 to the 10 such photons to create a signal in an antenna. These photons act together like a wave to create that effect because there's so many of them. On the other hand, gamma rays are so energetic that a single gamma ray can be detected. So if that's the case, if it's just kind of how energetic they are, and so thus our ability to perceive their particle-like properties, perhaps things that act like particles really are waves. So here comes the idea of the man shown here in the picture. In his doctoral dissertation in 1924, Louis de Broglie postulated that because photons have wave and particle characteristics, perhaps all forms of matter have both properties as well. This highly revolutionary idea had no experimental confirmation at the time. According to de Broglie, electrons, just like light, have a dual particle wave nature. Okay? So it would look something like this. All right? Here is the relationship between energy and momentum for a photon. Okay? So here we have the momentum of a photon. And we know that E, the energy of a photon, is hf. And so that means that we could express the momentum as hf over c, for example. Okay? Like so. Right? So we can then solve, right? Exactly. So we have hc over c lambda, or h over lambda. So this is the momentum of a photon, Planck's constant over the wavelength. Any number of different ways to write it. Again, we could write it as hf over lambda as well. All right. So for this equation, you can see that the photon wavelength can be specified by its momentum. De Broglie suggested that all material particles with momentum p should have a characteristic wavelength, lambda equals h over p. Okay? So de Broglie proposed that you can take that idea and apply it to not just photons. So it looks something like this. But here's the difference. For particles other than photons, they would have mass. And so then the momentum, p, wouldn't be E over c, because any particle other than the photon wouldn't be traveling at the speed of light, but instead would have the more classical form, mv. So we kind of have a hybridization of classical representation of particles with momentum mv, okay? And, well, the more quantized nature of the universe, this duality of both light and matter, okay? Because this momentum of a particle of mass m and speed v is mv, the Broglie wavelength of a particle is given by that relationship, okay? So then this idea, that right there would be the de Broglie wavelength. And we say that term if we're referring to the wavelength of matter. So for example, small things like electrons and protons have an associated wavelength with them, okay? So again, this is a big jump in ideas. So far we've been talking about light as being not just a wave but a particle, but now we're talking about things that we absolutely have always assumed are particles, like electrons and protons, but treating them as waves, okay? And so an electron would have its own wavelength, okay? De Broglie further postulated that the frequency of matter waves, or waves associated with particles having non-zero rest energy, obey the Einstein relationship for photons. So we also show that they have a frequency. All right, and so this would be the total energy of the particle divided by Planck's constant would give us the frequency of that particle. Okay, but is this just all, speculation, or do particles really behave like waves? So the dual nature of matter is apparent in these last two equations, because each contains both particle concepts like mv and e, and wave concepts like lambda and f. The fact that these relationships have been established experimentally for photons made the de Broglie hypothesis that much easier to accept. And the Davison-Germer experiment in 1927 actually confirmed de Broglie's hypothesis. Right? So we've known for almost 100 years that indeed particles can behave like waves, by showing that electrons scattering off crystals form a diffraction pattern. the regular spacing planes of atoms and crystalline regions of a nickel target act as different diffraction gratings for electron matter waves. All right? So true or false? As the momentum of a particle of mass m increases, its wavelength increases. False. M actually causes a decrease in wavelength. The larger the mass of the particle, the shorter and shorter the wavelength. So if you have something that's really massive, like the mass of a dust particle, for example, it's so massive relative to tiny things like electrons and protons that its wavelength is so short that we could probably never measure it. So it's only things of very small mass that have reasonably long wavelengths that can be experimentally measured in the laboratory. A non-relativistic electron and a non-relativistic proton are moving and have the same de Broglie wavelength. Which of the following are also the same for the two particles? Well, it turns out only their momentum. Okay? So if they have the same wavelength, they must have the same momentum. And we know that because lambda equals h over mv, or I suppose more importantly, lambda equals h over p. So if you have a particular wavelength, you also have a particular momentum. But we can show here, if your m is different, then your v is going to be different. Okay, so they will have different velocities. If they have different velocities, then they must have different kinetic energies, and their frequency is dependent on the total energy, and their total energy includes their rest energy, so that would be different for the two as well. So the only thing they share, if they share the same wavelength, is their momentum. Pretty interesting, right? So the major application of this idea now, something I kind of had hinted at before, was the idea of the electron microscope. So a particular device that relies on the wave characteristics of electrons is the electron microscope. So obviously we're so comfortable with the idea of electrons as waves that the electron microscope is a cornerstone of kind of modern laboratory technology. A transmission electron microscope used for viewing flat, thin samples is shown in the figure. It is similar to an optical microscope, except that the electron microscope has a much greater resolving power because it can accelerate electrons to very high kinetic energies, giving them very short wavelengths. No microscope can resolve details that are significantly smaller than the wavelength of the radiation used to illuminate the object. That's always the restricting factor. Just think about our equations for resolution power. They're all functions of the wavelength. Okay, so with light, we're limited to particular wavelengths, especially visible light. Here, we're going to be limited to particular wavelengths, but they're going to be much shorter wavelengths as the wavelengths of electrons. Typically, the wavelength of electrons in an electron microscope are smaller than the visible wavelength by a factor of about 10 to the negative 5. Right? So this is a microscope that can view things that are 100,000 times smaller than an optical microscope. The electron beam in an electron microscope is controlled by electrostatic or magnetic deflection, which acts on the electrons to focus the beam onto an image. Due to the limitations in the electromagnetic lenses used, the improvement in resolution over light microscopes is only about a factor of 1,000 instead of 100,000. 2 orders of magnitude smaller than what you might expect by the electron wavelength. Rather than examining the image through an eyepiece, as in an optical microscope, the viewer looks at an image formed on a fluorescent screen as shown in the photo. All right? So we need an extra kind of level of interpretation of that data because we can't visually see the electrons. Our eye doesn't register electrons hitting the retina or anything. And so we need to then turn that into an image we can see. Now, the biggest question, the one that I'll include an example of this, is, okay, well, great, we're using electrons. They have a shorter wavelength. It allows us to see smaller things. But weren't we just talking about light that has shorter wavelength? Why not just use X-rays, right? X-rays have shorter wavelength. Couldn't they do the same thing as an electron? But here's the thing. Do a photon with wavelength, say 1 nanometer, and an electron with wavelength 1 nanometer, do they both have the same amount of energy associated with them? No, not at all. It turns out light of wavelength on the order of 1 nanometer, this is just an example, compared to an electron with a wavelength on the order of 1 nanometer, well, it turns out the light has way more energy per wavelength, or at a particular wavelength. So the X-rays would be very destructive to the sample, whereas the electrons can have that short wavelength without as much energy. That right there is the crux of it. But of course, seeing it numerically will hopefully help that sink in when I show you all in a subsequent video and set of lecture notes. All right, so a couple last ideas to wrap up this lecture. The wave function. So in 1926, the Austrian-German physicist Erwin Schrödinger proposed a wave equation that described how matter waves change in space and time. The Schrödinger wave equation represented a key element in the theory of quantum mechanics. It is kind of one of the big governing equations of quantum mechanics. It's as important in quantum mechanics as Newton's laws are in classical mechanics. Schrödinger's equation has been successfully applied to the hydrogen atom and many other microscopic systems. Solving Schrödinger's equation, which is beyond the level of this course because it is a second-order partial differential equation, determines a quantity called the wave function. Those are the solutions to the differential equation. They're denoted by the Greek letter phi, psi, not phi, this misspoke. Each particle is represented by a wave function. Psi depends on both the position and time, so it's a function of two variables. Once psi is found, psi squared, so if you take the magnitude of this squared, gives you something called the probability distribution or probability function. All right, and this is the probability per unit volume of finding a particle in any given region. To understand, we could return to the idea of Young's experiment involving coherent light passing through a double slit. First, recall that the intensity of the light beam is proportional to the square of the electric field strength E associated with the beam. According to the wave model of light, there are certain points on the viewing screen where the net electric field is zero as a result of destructive interference of the waves from the two slits. Because E is zero at these points, the intensity is also zero, and the screen darkens there. Likewise, at points on the screen where constructive interference occurs, E is large and the intensity is high. So these locations are bright. But if we don't think about it as waves, and we instead think about particles, we can get the same results. Let's consider the same experiment when light is viewed as having a particle nature. The number of photons reaching a point on the screen per second increases as the intensity brightness increases. So the number of photons that strike a unit area on the screen each second is proportional to the square of the electric field. From a probability point of view, a photon has a higher probability of striking the screen at a point where the intensity is greater, and a lower probability of striking the screen when the intensity is low. So we see that the beauty of this idea of having a wave equation with wave functions and probability functions as solutions to the wave equation, it allows us to think about particles behaving like waves and waves behaving like particles. And it is, like I said, a cornerstone of modern physics. So our last topic builds off of this idea of probability, and it is the uncertainty principle, or Heisenberg's uncertainty principle. So something that is kind of known in everyday parlance. Okay, so according to classical mechanics, it's possible in principle to measure, for example, the position or speed of a particle with arbitrarily small uncertainty, right? So everything with the right experiment should be able to be measured almost exactly. Quantum theory, on the other hand, predicts otherwise. In 1927, Werner Heisenberg, who lived from 1901 to 1976, introduced this notion, which is now known as the uncertainty principle. If a measurement of the position of a particle is made with a precision delta x, so this would be the precision, then and a simultaneous measurement of linear momentum is also made with precision delta p, okay, and that's in the same direction, so delta px. The product of the two uncertainties can never be smaller than Planck's constant divided by 4 pi. This is the absolute limiting precision. In other words, it is physically impossible to measure simultaneously the exact position and exact linear momentum of a particle. If delta x is very small, then delta momentum is large, and vice versa. Okay? So if you give up precision in position, you gain precision in momentum, thus you get a more precise velocity. But if you give up precision in momentum, like you don't know the velocity very precisely, then you may be able to know the position very precisely. But you can't know both. The more precisely you know the velocity, the less you know about the precision, and vice versa. All right? So let's do a thought experiment to understand the physical origins of the uncertainty principle. Because otherwise it does kind of just seem like I'm just telling you that's the fact, right? This thought experiment was introduced by Heisenberg. Suppose you wish to measure the position and linear momentum of an electron as accurately as possible. You might be able to do this by viewing the electron with a powerful light microscope. For you to see the electron and determine its location, at least one photon of light must bounce off the electron, as shown in the figure on the left, and pass through the microscope into your eye, as in the figure on the right. When it strikes the electron, however, the photon transfers some unknown amount of momentum to the electron. In other words, in the process of locating the electron very accurately, that is, by making delta x very small, the light that enables you to do that would become more intense and thus would bounce off the photon, or would bounce off the electron in a more high energy way, and then tell you less about the velocity of the electron. Right? So you'd have to give up your understanding of its velocity by knowing exactly where it is. In other words, it is impossible to not interfere with a system in observing it. Okay? There's other ideas that kind of relate back to this idea of uncertainty, and to a couple slides ago to Schrodinger's wave equations and the kind of the governing equation of quantum mechanics. And that is that if you observe a system, then you cause that system to take a certain form. If you never observe it, then the form is unknown, and then it could take multiple forms. But once you observe it, that form is locked in place because you had to do something to observe it. And by doing it, you set up a chain reaction that then is real, right? You've set a certain state. The jargon term for that is the collapsing of the wave function. The best known case of that is the Schrodinger's cat thought experiment, that the cat can either be alive or dead, trapped in a box with a certain poisonous isotope that has a certain basically probabilistic chance of tunneling out of its container and thus poisoning the cat. So that's the idea, is that the probability is undetermined until the act of observing puts energy into the system, thus setting a series of events into action that result in a particular case. Okay? So the incoming photon, back to our thought experiment, the incoming photon in our thought experiment has momentum h over lambda. As a result of the collision, the photon transfers part or all of its momentum along the x-axis to the electron. This means that the uncertainty in the electron's momentum after the collision is as great as the momentum of the incoming photon. Also, because the photon has wave properties, we expect to be able to determine the electron's position to within one wavelength of the light being used. So multiplying these two uncertainties gives the following results. All right, so that's where the h comes from for the limiting factor, right? So the fact that we're saying that delta x times delta p has to be less than or equal to h over 4 pi, that h isn't just there because it's like, oh, Planck's constant comes up a lot in quantum mechanics. It comes directly from the quantization of a single photon of light. The absolute minimum case, because there'd be no way to convey information without bouncing at least one photon of light off of the thing you're trying to observe. All right? And so then you might say that the case would always have to be greater than or equal to h, but in reality it turns out that that is a simplification of the inequality, and the accurate version ends up being h over 4 pi. Okay, we won't explain the origins of that, but it turns out that is the further specification. Okay? And this applies to not just position and momentum, but also time and energy. So we could set up a similar inequality that tells us that the uncertainty in time multiplied by the uncertainty in energy is also always going to be greater than or equal to h over 4 pi. Okay, so those are the two uncertainty equations. So quick summary, what have we looked at? We looked at black body radiation and Wien's law. We looked at the quantization of Planck's resonators, or just the fact that the energy that's emitted from a black body is quantized. Okay, we'll talk a lot more about quantum numbers in the next chapter. We talked about the photoelectric effect, which included the maximum kinetic energy of freed electrons, the incoming energy of the light, and the work function of the metal. Okay, this equation in particular is probably going to be the biggest one that we're going to see in computational problems from the chapter. What else did we talk about? We talked about diffraction of X-rays off of crystals, all right, including the minimum wavelength that is produced in an X-ray production chamber, and then the actual diffraction, which was similar to thin film interference in concept and mathematical form. We talked about the Compton Effect, okay, which includes the scattering, or which specifically describes the scattering of photons off of electrons at rest. It is specific to electrons at rest. So you can kind of think of this equation here is defined by metals with a lattice like so, and some spacing between the atoms in that lattice, whereas the Compton effect is all about some electron just sitting in space and being crashed into by a photon. Lastly, or almost last, we talked about the dual nature of light and matter, which introduced the Broglie wavelength, which is the wavelength of matter, such as the wavelength of electrons and protons, okay, which we then showed some similarities to how that relates to the energy of a photon, very similar, except it includes MV, which we would never see for a photon. And lastly, we introduced, in terms of what we talked about, the wave function, but lastly, in terms of equations, we introduced the uncertainty principle in its two forms and talked a bit about justifying why it should make sense. All right, well, that summarizes all of the chapter, and hopefully it seems interesting, and you can continue to get some practice with some problems and some further reading, and thank you for watching.